should not be here. Neither should I. Neither should the chair you're sitting in, the screen you're watching this on, the planet beneath your feet, or the star that keeps it warm. None of this should exist. That is not philosophy. That is not poetry. That is the conclusion of one of the most precisely tested predictions in the history of science. Sasha Gunjur, a physicist at CERN who has spent over 20 years running experiments inside the largest machine ever built by human beings, said it plainly in 2024. Every measurement we make tells us the universe should be empty, just light. No atoms, no stars, no chemistry, no life, nothing. The reason is simple and devastating. When the Big Bang occurred 13.8 billion years ago, it should have created exactly equal amounts of two things, matter and antimatter. Every particle paired with its mirror twin, electron and positron, proton and antiproton, quark and antiquark, perfectly balanced, like two opposing armies of identical size marching onto the same battlefield. And when matter and antimatter meet, they do not coexist, they annihilate completely. Both particles vanish in a flash of pure energy. No survivors, no remnants, just gamma rays. If the Big Bang produced equal amounts of both, then within the first few seconds of the universe's existence, every particle of matter should have found its antimatter counterpart, and the two should have erased each other from reality. The entire cosmos reduced to a sea of cooling radiation. That's the prediction. That's what the math says. That's what every experiment at every energy level we've ever tested confirms about how matter and antimatter behave. And yet, here we are, sitting inside a universe made almost entirely of matter. A universe with 100 billion galaxies, each containing 100 billion stars, each forging heavy elements inside their cores, some of those elements forming rocky planets, and at least one of those planets producing someone who just asked, why does anything exist? Something broke the symmetry. Something, in the first fraction of a second after the Big Bang, tipped the scale. Not by much. The imbalance was absurdly small, as for every billion antimatter particles, there were 1,000,000,001 matter particles, one extra grain of sand on one side of a cosmic scale, but that one extra particle per billion, that tiny, almost negligible asymmetry, is everything. It's you. It's me. It's the entire visible universe. Physicists call this the baryon asymmetry problem, and it has been an open wound in fundamental physics for over 50 years. We know the universe is made of matter. We know it shouldn't be. We do not know why. For decades, the best hope for solving this was a concept called CP violation. CP stands for charge parity symmetry. In simple terms, it's the rule that says if you swap every particle for its antiparticle and flip the universe like a mirror, the laws of physics should still work the same way. If CP symmetry were perfect, matter and antimatter would behave identically under all conditions. No preference, no asymmetry, no universe. But in 1964, two physicists at Brookhaven National Laboratory, James Cronin and Val Fitch, discovered that CP symmetry is not perfect. They were studying a particle called a kaon, a strange, unstable thing that exists for only about 100 millionth of a second before decaying. Kaons come in matter and antimatter versions, and Cronin and Fitch found that the two versions decay at slightly different rates. Not by a lot. The difference was tiny, but it was real. Matter and antimatter were not perfectly identical. For the first time, physics had proof that the universe plays favorites. Cronin and Fitch won the Nobel Prize. The discovery was hailed as the first step toward explaining why matter won the war, except it wasn't enough. Not even close. The amount of CP violation found in kaon decays was orders of magnitude too small to explain the baryon asymmetry. It was like finding a single drop of water at a crime scene and being told to account for a flood. The mechanism was real, but it was absurdly weak. You'd need CP violation millions of times stronger to generate the universe we observe. So physicists went looking for more of it. They built bigger machines, smashed particles harder, searched in heavier, more exotic particles. In 2001, two enormous experiments, Babar at Stanford and Bell in Japan, confirmed that CP violation also exists in a heavier particle called a B meson. Again, matter and antimatter decayed differently. Again, the effect was real. Again, it was too small. Dramatically, hopelessly too small. And then the Large Hadron Collider turned on. The LHC, buried 100 meters beneath the Swiss-French border near Geneva, is a 27-kilometer ring of superconducting magnets cooled to temperatures colder than outer space. It accelerates protons to 99.9999991% the speed of light and slams them into each other roughly 1 billion times per second. It is, by a considerable margin, the most complex and expensive scientific instrument ever constructed. One of the LHC's main detectors, a machine called LHCb, was built for exactly this question. Its sole purpose is to catch the subtle differences between matter and antimatter. It watches billions of particle decays, catalogs the angles and energies and lifetimes of the debris, and hunts for any whisper of asymmetry that might explain why the universe isn't empty. In 2019, the LHCb collaboration announced a result that stopped the field cold. They had found CP violation in a particle called the D meson, a particle containing a charm quark. This was the first time CP violation had ever been observed outside the Kaon and B meson systems, a new source, a new crack in the symmetry. The physics community held its breath. But once again, the size of the effect was too small. The asymmetry was real, measurable, statistically significant, and utterly inadequate to explain the missing antimatter. Think about what that means for a moment. We now have 3 independent particle systems in which nature demonstrably treats matter and antimatter differently. 3 separate experiments, 3 different particle families, decades of data, and the total combined CP violation from all known sources in particle physics accounts for less than 1/1000th of the asymmetry needed to produce the universe. It's as if someone told you that a dam broke and flooded an entire valley, and you spent 40 years searching every inch of that dam, and the only damage you could find was a hairline crack barely visible to the naked eye. The crack is real, the flood is real, but the crack cannot possibly explain the flood. So something else must have happened. In 1967, the Russian physicist Andrei Sakharov, who would later become famous as a dissident and human rights activist, outlined 3 conditions that the universe would need to satisfy in order for the antimatter imbalance to arise naturally. First, there must be processes that violate baryon number, meaning reactions that can create more matter than antimatter or vice versa. Second, there must be CP violation. Third, these processes must occur out of thermal equilibrium, during a period when the universe was changing so rapidly that the reactions couldn't settle into a balanced state. The standard model of particle physics technically satisfies all 3 conditions. Baryon number violation is possible through a quantum process called a Sphaleron transition. CP violation exists, as we've seen. And the early universe was certainly out of equilibrium during phase transitions, but when you plug the actual numbers from the standard model into the calculation, the result is a universe with roughly 0 net matter. The ingredients are there, the recipe is there, but the oven isn't hot enough. The standard model's version of these 3 conditions produces an asymmetry so absurdly small that it might as well be nothing. We would not exist. And here is where it gets genuinely unsettling, because the standard model is not some rough draft. It is the most successful quantitative theory in the history of science. Its predictions have been verified to 12 decimal places. It predicted the existence of the Higgs boson decades before it was found. It describes the behavior of every known particle and 3 of the 4 fundamental forces with a precision that borders on the unreasonable. And yet it cannot explain why you are alive. It cannot explain why atoms exist. It cannot explain why the universe contains anything at all. The most precise theory ever devised by human intelligence predicts a cosmos that is empty. And the cosmos responded by producing someone capable of noticing the prediction is wrong. So physicists started looking beyond the standard model. If the known particles can't generate enough asymmetry, maybe unknown ones can. One of the most promising ideas is called leptogenesis. It proposes that the asymmetry didn't start with quarks at all, but with a different family of particles, leptons, the family that includes electrons and neutrinos. Here's the idea. In the extremely early universe, fractions of a second after the Big Bang, there may have existed extremely heavy versions of neutrinos. Not the ghostly, nearly massless neutrinos we detect today, but their ancient ancestors. Particles so massive they could only exist in the absurd energy conditions of the newborn cosmos. These heavy neutrinos would have been unstable, and when they decayed, they may have done so asymmetrically. Slightly more leptons than antileptons, a tiny excess imprinted into the fabric of the universe before it was a second old. Then, through Sphaleron transition, those quantum processes that can convert between baryons and leptons, the total amount of matter and antimatter in the full picture, our universe plus its temporal mirror, is perfectly balanced. We just happen to live on one side of the mirror. The antimatter isn't missing, it's on the other side of time. This isn't fringe science. Boyle and Turok's paper was published in the Annals of Physics and has generated serious theoretical discussion, but it is, as of now, untestable. We cannot observe backward through the Big Bang. We cannot confirm or deny the existence of a temporal mirror. It's an answer that satisfies the math and completely defies the experiment. Meanwhile, the experimental side is about to get a massive upgrade. CERN's LHCb detector underwent a complete rebuild during the LHC's second-long shutdown and began collecting data again in 2022 with roughly 5 times the sensitivity of its original design. Over the next decade, it will accumulate an unprecedented data set of heavy particle decays, hunting for any deviation from the standard model's predictions. The upgraded experiment has already started delivering. In 2024, LHCb published the most precise single measurement of a CP violating parameter ever made, a quantity called the CKM angle gamma, nailing it down to a precision of about 4 degrees. That might sound imprecise, but in this context, it represents decades of incremental progress compressed into a single detector upgrade. And here's the thing that keeps physicists awake at night. If the upgraded LHCb and DUNE, and the next generation of Kaon experiments at J-Park in Japan, and the muon experiments at Fermilab, if all of them come back and confirm that the standard model is correct, that CP violation is exactly what the equations predict and not a fraction more, then we are in serious trouble. Because it would mean that the mechanism that created the universe is not contained in the physics we know. It would mean that something happened in the first moments of existence that our best theory cannot describe. Not because the theory is imprecise, but because the theory is missing something fundamental. It's worth stepping back and appreciating how strange this situation is. We are not talking about a small puzzle at the edge of knowledge. We are talking about the existence of everything. Every atom in your body was once on the winning side of a war that we cannot explain. The hydrogen in the water you drank this morning was forged in the first few minutes after the Big Bang, from quarks that survived the annihilation year. And we do not know why those quarks survived. The oxygen in your lungs was fused in the core of a massive star that exploded billions of years before our sun was born. A star made of matter that shouldn't be here. The iron in your blood, the calcium in your bones, the carbon in your DNA, all of it traces back to that unexplained 1 in a billion excess. You are literally made of the leftover crumbs from a cosmic catastrophe that physics says should have left nothing behind. Andrei Sakharov outlined the conditions in 1967. Almost 60 years later, we have confirmed that nature satisfies them, but only barely and nowhere near enough. We've found the cracks in the symmetry, we just can't find the hammer that swung hard enough to break it. Some researchers like Hitoshi Murayama at UC Berkeley believe the answer lies in an entirely new sector of particles, supersymmetric partners or heavy sterile neutrinos, that existed only in the extreme conditions of the early universe and have since decayed beyond our reach. Others, like Juan Maldacena at the Institute for Advanced Study, have explored the possibility that the asymmetry could be connected to the quantum properties of space-time itself. That the answer isn't in particles, but in the fabric of reality. We don't know yet. That's the honest truth. The most important question in fundamental physics, why does anything exist, remains open. But here's what gives me hope. Every time physics has reached an impasse like this, the resolution was not a minor adjustment. It was not a tweak. It was something nobody imagined. When the orbit of Mercury didn't match Newton's predictions, the answer was not a better version of Newtonian gravity. The answer was general relativity, a complete reimagining of what space and time actually are. When the ultraviolet catastrophe threatened to break classical thermodynamics, the answer was not a correction factor. It was quantum mechanics, a revelation that energy comes in discrete chunks and that the entire subatomic world obeys rules that would have seemed insane to 19th century physicists. The baryon asymmetry is that kind of problem. It's not a loose thread, it's a load-bearing wall. And when the answer finally comes, from DUNE or LHCb or an experiment that hasn't been designed yet, it is almost certainly going to change what we think matter is, what we think the Big Bang was, and possibly what we think time itself means. That leptonic asymmetry would have been partially transferred into a baryonic one. More matter than antimatter. Just enough. It's elegant. It's mathematically self-consistent. And it depends entirely on neutrinos doing something we haven't proven they can do, violating CP symmetry. Which brings us to the most ambitious neutrino experiments ever attempted. Deep underground in the mountains of central Japan, a detector called T2K has been firing beams of neutrinos and antineutrinos 295 kilometers through the Earth's crust to a massive underground detector filled with 50,000 tons of ultra-pure water. The experiment has one goal: measure whether neutrinos and antineutrinos change flavor, morph from one type into another's at different rates. If they do, that's CP violation in the neutrino sector. A new, potentially much larger source of the asymmetry that particle physics has been desperately searching for. In 2020, the T2K collaboration published results suggesting that the answer is yes. Their data showed a preference, not yet conclusive but strong, for neutrinos and antineutrinos to oscillate differently. The statistical significance was roughly 3 sigma. In plain language, there was about a 99.7% chance the effect was real and a 0.3% chance it was a fluke. In particle physics, 5 sigma is the gold standard for a discovery. 3 sigma is suggestive, tantalizing, not proof, not yet. But an even bigger experiment is coming. In the former Home State gold mine in Lead, South Dakota, 1,500 meters underground, the United States Department of Energy is building DUNE, the Deep Underground Neutrino Experiment. When operational, a beam of neutrinos will be fired from Fermilab near Chicago across 1,300 kilometers of rock and soil to 4 massive detector modules, each containing 17,000 tons of liquid argon cooled to minus 186 degrees Celsius. DUNE is designed to answer the CP question definitively. If neutrinos violate CP symmetry at a large enough level, DUNE will see it. And if they do, it would be the first direct evidence that leptogenesis could work. That the mechanism that created the matter in the universe operated through neutrinos, not quarks. But there's a catch. And it's a significant one. Even if DUNE confirms CP violation in neutrinos, it doesn't automatically solve the problem. Leptogenesis requires those hypothetical super-heavy neutrinos from the early universe, and their masses are estimated to be around 10 to the power of 10 to the power of 15 giga-electron volts. Energy scales so far beyond anything the LHC can reach that we may never produce them directly. We could confirm that low-energy neutrinos violate CP symmetry and still have no proof that their high-energy ancestors did the same. It would be like finding wet footprints leading away from the scene of the flood, pointing toward a suspect, but never being able to place the suspect at the dam. And that's not even the strangest part. In 2023, a team at CERN's ALPHA experiment did something that would have been considered science fiction 20 years ago. They made antimatter, actual antihydrogen atoms, and dropped them. Literally. They wanted to know if antimatter falls down like regular matter or if gravity treats it differently. The question sounds almost childish. Of course, antimatter falls down. General relativity treats mass as mass, regardless of whether the particle is matter or antimatter. Every theoretical framework we have predicts that antimatter should respond to gravity exactly the same way, but nobody had ever tested it, because antimatter is insanely difficult to work with. An antihydrogen atom, the moment it touches any ordinary matter, the walls of its container, a stray molecule of air, anything, annihilates. Gone. Poof. You have to trap it in a magnetic bottle in a near-perfect vacuum at temperatures close to absolute zero and hold it there long enough to watch it move. The Alpha team managed it. They trapped about 100 antihydrogen atoms, released them, and watched which way they fell. The answer? Down. Antimatter falls down. Gravity pulls on it the same way it pulls on everything else. General relativity was right, but that result, oddly, makes the mystery worse. Because if gravity doesn't distinguish between matter and antimatter, then gravity can't be responsible for the asymmetry either. One more door closed. One less explanation available. Some physicists have gone further, way further. A proposal called the CPT Mirror Universe, developed by Latham Boyle and Neil Turok at the Perimeter Institute in Canada, suggests that the Big Bang didn't just create our universe expanding forward in time. It also created a mirror universe expanding backward in time on the other side of the Big Bang, a universe made entirely of antimatter running in reverse. In this picture, the asymmetry isn't really an asymmetry at all. If you could somehow step outside reality and look at this moment, this exact sliver of history, you'd see a species made entirely of matter that shouldn't exist, using machines built from that same matter to figure out why any of it is here. Running neutrino beams through 1,300 kilometers of rock, trapping antimatter atoms one at a time in magnetic bottles, smashing protons together 1 billion times a second underground in Switzerland, all to answer a question that every atom in their bodies is evidence of. That's either the most profound thing a civilization can do or the most absurd. And I think, like most things worth doing, it's both. The universe shouldn't exist. It does. And nobody knows why. But the fact that we noticed, the fact that matter organized itself into brains capable of asking the question, might be the most extraordinary thing about the answer whenever it comes. Thanks for watching, and I'll see you in the next one.